Greetings. I'm Narayanan Komerath. My co-authors are Adarsh Deepak and Ravi Deepak of the Taksha Institute. I am speaking from Thrissur, Kerala in India, while they are in Hampton, Virginia, USA. So thanks for enabling us to present at this conference, which is in a virtual mode. And we want to talk about an aerospace approach to counter climate change. A quick summary. We are trying to collect climate data while reducing atmospheric heat retention. Our HAIL, or High Altitude Long Endurance architecture of reflective vehicles, is called the glitter belt, indicating what is seen of these, if at all, from space, if you look with the telescope down below, which is all that will be seen of these things in actual operation. Swarms of these meteorology platforms can be scaled to reduce atmospheric heat retention. They are designed for 30.5 kilometers or 100,000 feet altitude, 12-hour nighttime glide staying above controlled airspace, rendezvous and swarm operations, and distributed antenna applications. Of course, all of these pose unique challenges, tough challenges, but they are shown to be feasible, which is in my view, the job of the concept developer. The details, of course, will come, and they will come later. Conceptual design, small-scale design, build, flight testing, and dynamic flight simulation are all used to remove uncertainties and reduce the costs and derive system properties at an early stage. The scale-up, if any, will occur when stakeholders are all ready. Given the international will, global warming can be reduced in a verified, safe, and reversible manner, satisfying all guidance from the national academies. Net positive atmospheric heat retention rate is not decreasing despite our best efforts for the past 20 years. Most nations, in fact, care a lot more about the United Nations Sustainable Development Goals, where climate action comes number 13 on a list of 17. Then they do about the carbon reduction, which is about all we hear about regarding climate change. It's an obvious idea to reflect some of sunlight back into space, but the National Academies of Sciences has warned very clearly about all the dangers there and laid out clear guidelines on how to avoid these dangers. Our objective is to develop a safe, well-understood option to reduce net heating that matches the priorities of most nations and does not harm anyone. Our approach comes under mitigation technologies, and we are in fact proposing the much despised option of reflecting sunlight. We summarize why this is not so horrible. It's actually feasible, technically feasible, economically and politically viable, and scientifically responsible, ethically responsible. We start with meteorology for climate simulation. We propose a scheme for nature credits, expanded from the very good idea of carbon credits and carbon markets, recognizing the UN's Sustainable Development Goals. So this enables each nation to do what makes sense for their national priorities. Placing reflectors in space, as many people think this is all about, is just not feasible. It's so far out impractical that it's not worth discussing, and I've shown why. But one can float reflectors at 30.5 kilometers, or 100,000 feet, where they can be held using aerodynamics or aerostatics. We propose 25 micron aluminized mylar sheets, aluminized on the upper surface, with an infrared absorptive layer below to pick up and transmit nighttime radiation. So these are long endurance, solar photovoltaic powered swarms of flying wings. Over 98.5% of the infrared is reflected, at least in lab tests, even at shallow incidence angles. Our architecture uses just two types of vehicles. The launchers are called flying leaflets or FLTs. These are biplanes where the rolled up sheet is the upper wing and a photovoltaic covered vehicle below has electric propellers. A flying leaf is assembled at altitude from 11 of these flying leaflets with 8 of the 11 propulsive wings return to base to launch more sheets. The large span of the flying leaf is needed to provide enough aspect ratio to reduce induced drag and to permit indefinite endurance, able to glide above controlled airspace through more than a 12-hour night. As I define presently, indefinite endurance means surviving 12 hours, and I'll explain why. 12-hour nights, and I'll explain why as we go along. So how crazy is this? Not at all crazy, as it turns out. We have been looking at this for some years. It's not an idea that came up yesterday. You need about 500 million launches over, say, a 10-year period to cut atmospheric heat retention rate by 50%, or 2 billion launches to reverse global warming as fast as it is rising now. There will be global cooling at the same rate as global warming is happening now, in the absence of any other useful initiative that is actually doing anything other than holding conferences. So, of course, we think we don't have to do anything close to this, that much of the problem will be solved by other means, but we can buy time, number one, for other measures, and number two, provide confidence that we can solve the whole problem. So how big is this? 500 million launches, 2 billion launches, what are you talking about? Compare that to just one type of airliner, the Boeing 787. Okay, there are enough of those things that the mass launched in our proposal is only about what the Boeing 787 launches account for over a 3-year period. Okay, so it's just a question of international will. The cost per square meter of reflector comes out about the same as the cost of equivalent mass of jet fuel, cost of putting up the per square meter of reflector. So it's not horrendous, but it's not small either. I'm showing 3 generalized results, which are really independent of the precise details of the vehicles. The 2 figures on the right show that in order to stay above 60,000 feet or 18.3 kilometers through a 12-hour night, one should have a wing loading, that is the gross weight divided by the lifting surface area, of under 1.25 newtons per meter squared. That's very low, of course. Boeing 787 probably has around 8,000 newtons per meter squared, but it travels at near the speed of sound, 300 and something meters per second, whereas we travel about 10 meters a second. And a profile drag coefficient of not more than 0.02. That part is quite achievable. With these, we see that long endurance is possible, still requires wingspans larger than 30 meters. So there is a fairly narrow range of design parameters where things do work. And the idea is to be in that space and take out all the uncertainties. The deployment sequence is shown here. So on a calm summer morning, unfortunately you can't do this if it's very windy, the flying leaflets take off and climb to 100,000 feet. Deploying the reflective sheet gradually as the flying leaflet rises into the calm stratosphere. They're not going to get ripped up by turbulent gusts and so forth, as some people have worried about. 11 of these flying leaflets then join their sheets wingtip to wingtip. That has to be automatic rendezvous, which is has been demonstrated with flying vehicles. And 8 of the propulsive wings then detach and return to base before it gets too dark, leaving 3 to propel the flying leaf the next day. Flying leaves then gather in swarms to carry out their operations. So these have unprecedented applications once you can do this. They have indefinite endurance. And again, I use the term indefinite endurance to say we can keep these up there as long as we wish. Not going to be infinity, something is going to get destroyed eventually, but we don't see any real need to bring them down very quickly. And global range. if you have a steady 1 meter per second drift northwards or southwards as part of your ordinary velocity component, the swarms can stay under the peak summer sun all year, crossing the equator twice. So the longest night that has to be encountered is only 12 hours, and that is while crossing the equator. Click. Oh, sorry. I believe this thing will show you something while I'm speaking. We benchmarked against other high altitude long endurance concepts. Note that we get very low wing loading because of the lift from the thin sheets themselves. The sheets are not payload, they are the lifting surfaces. Other aspects are briefly listed here, and we have used wind tunnel testing, flight testing, all sorts of calculations, combined with design analysis and flight simulation. The first 8 meter span flight test model is being planned to be built by a leading university for coastal flight testing. So these things really do fill an important gap in current meteorology tools, and they can collect data that simply can't be collected any other way. The National Academies, in their report in January 2021, set out concerns and guidelines for projects that reflect sunlight. This is precious guidance. It scared me a little bit seeing the title of the report, but reading through it, I said, wow, this is exactly what we need. Because it informs and demonstrates how our process more than satisfies all these concerns. This slide summarizes our process to date, and you can see that we've been publishing the progress as we have been moving along. The trail of publication sets out different aspects of the progress. There is a long way to go. No illusions about that. But we also have made quite a bit of progress. I believe that all the objections and uncertainties that I have heard have been addressed, and there is a straightforward path, not an easy path, but a straightforward path to implement our architecture and solve the problem. So in conclusion, we have shown that atmospheric heat retention can be reduced, stopped, and reversed through a carefully monitored, affordable, and reversible process. Reversible, by reversible I mean that if you find out that this is very wrong, you can actually not just pull it down, but you can actually turn the sheets upside down and send in more sunlight, or if the earth suddenly starts cooling, you could turn the sheets upside down and actually bring in more heat. So it is reversible. More to the point, it is totally under control, and we'll be monitoring it as we do it, and so any concerns can be addressed right away. Our architecture proactively resolves all concerns, starting with a unique ability to continuously acquire highly resolved data over most regions of the planet, including, most importantly, the huge expanse of Southern Ocean, where it's very difficult to have any other means of meteorology other than flying spacecraft, which are just too fast and too high above the oceans. Conceptual design features have been summarized, and system features have been derived from those. Ground and flight testing have been combined with flight simulation to move ahead with reducing uncertainty. A consortium structure is being established to facilitate global participation. We hope you participate too. Given international will, and it's our planet, remember, atmospheric heat retention can be stopped and reversed in our time at an affordable cost and without destroying economies or doing anything of that sort. So the Taksha Institute supported this work, for which we are very grateful. I'm just showing part of the flight simulation process where one learns to keep the vehicle stable, which we did eventually. But I'm showing you the nature of a flying leaf vehicle here as we go along. So thank you very much. That concludes my presentation, and I'll be very happy to take questions.